Hi, this is our project on turbo machines. Our group members are Stephanie Price, myself, Elise Pritchard, Manny Sanchez, and Seamus Wade. So this is just a little intro to turbo machines. Turbo machines are mechanical devices with blades that are then attached to a rotor, and that extracts energy from a fluid, which is a turbine, or it adds energy to a fluid, which is a pump. Energy is a result of the dynamic interaction between the blades and the fluids can either be in the forms of gas, vapor, or liquid. Turbo machines either have a casing that causes an internal flow inside, or they're open with no casing like a windmill or a fan. There are three types of flows: axial, mixed, or radial, and the type depends on the direction of the fluid relative to the rotor axis as the fluid passes through the blades. Basically, if the blade does work on the fluid, then that would be classified as a pump. And if the fluid does work on the blades, then that would be classified as a turbine.
All right, so here we have the basic principle of the velocity profiles when it comes to turbo machines. The overarching equation being V equals W plus U, where V is the absolute fluid velocity, the velocity of the fluid relative to an outside viewer. W, which is the relative velocity, the velocity of the fluid relative to a blade on the fan, and U, which is the blade speed, which is also equal to the angular velocity times the radial distance from the fan axis. Here's a quick 2D representation of a single fan in a turbo machine. And ideally, we assume that blade motion is uniform. So the initial and the final U for U1 and U2 are equal. The relative velocity vector aligns with the blade pointing in the direction of the flow, and W and U are vectors, so the vector sum ends up making a triangle. So you can see those in the triangles with at point 1 and point 2. Another thing to note is is theta, which is the angle relative to the tangent of the blade. So as you can see at V1, there is no the velocity isn't angled, while at V2, it is angled, and we'll explain that more in the next slide. So the angle of V2 comes in importance when determining whether a turbo machine is a pump or a turbine. If the angle changes within the direction of the fan motion, then the fan performs work on the fluid and therefore is a pump. Meanwhile, if the angle changes in the opposite direction of fin movement, then the fluid does work on the fin, making it a turbine.
So I'm going to be talking about the angular momentum. We know that work equals force times angular displacement. And so if the shaft work and rotation are in the same direction, it's a pump. And if the shaft work and rotation are in opposite directions, it's a turbine. We have the Euler turbo machine equation, and shaft torque is positive if it moves in the same direction as rotation. We also know that shaft power equals the shaft torque times the angular velocity, and the shaft power will be positive when moving in the same direction as angular velocity. And then after some simplifications, we get the shaft power per unit mass equation as seen right there. So some characteristics of an effective pump include that the kinetic energy increases, there's an outward radial flow, and a decelerated flow in blade passages.
So I'm going to be talking about one of the most common types of pumps, which is the centrifugal pump. The most common type of radial flow, which is the centrifugal pump. It has two main pieces, which are the impeller and then a casing around it. The impeller is just blades arranged in a pattern around a shaft, and these are often curved. As the impeller rotates, the fluid is sucked into the eye of the casing and flows radially outward. Work is done on the fluid by the rotating blades. Initially, this causes an increase in kinetic energy and pressure, but as the fluid flows to the casing, the kinetic energy is then converted to a further pressure increase. There's different impeller types. The first is an open impeller, so the blades are arranged on a plate and uncovered on one side, and those are seen in the bottom of the screen. And then an enclosed impeller is when the blades are covered on both ends, and that's also seen at the bottom of the screen. Single suction is when the fluid enters the eye on one side of the impeller, and then double suction is when fluid enters the eye on both sides of the impeller. And these are a little more favorable because they reduce the thrust on the shaft and the inlet velocity overall. There's another two types of pumps, which are single or multi-stage. Single pumps just have one impeller inside a singular shaft, but multi-stage pumps have several impellers in one shaft. And then these are done in stages. So the fluid goes from impeller 1 to impeller 2 to impeller 3. And then there's a steady flow rate throughout all those pumps. And then but the pressure increases with the stages. So at the end, this causes a large discharge pressure, which can be called head. Pump performance curves. These are characteristics about pumps given data that's determined experimentally through tests. So this is the picture that you see on the right. This is what actually helps the engineer when incorporating pumps into a given flow system. And then another thing that helps them is the efficiency of the pump. So this is calculated by power gained by a fluid over the shaft power of the pump. Overall efficiency as seen in that equation has to incorporate things like hydraulic, mechanical, and volumetric efficiencies.
Axial flow pumps are often called propeller pumps. They're most commonly used for drainage and irrigation. There are two types of blades, the rotating, which is also called a rotor, and a fixed, which is the stator. They're often used in alternating rows. In some axial flow pumps, you'll find the stator blades by the inlet and outlet of the pump to straighten and guide the flow respectively. These pumps are very similar to the centrifugal pumps. However, the flow characteristics are quite different. Upon shutoff, centrifugal pumps fall to 180 horsepower, while axial flow pumps increase to 520 horsepower. The axial flow pumps are less efficient at design capacity, so to compensate, they're constructed with adjustable blades. The centrifugal pumps are started with the system closed, but axial flow pumps should be started with the system open to avoid power spikes at zero flow. Some left ventricle assist devices are axial flow pumps, which are inside the heart. They're used to help pump blood within the broken pumps that are beyond repair. Mixed flow pumps are combination of the centrifugal pumps and the axial flow pumps. These pumps were designed for applications that require specific speed intermediate to those of the centrifugal and the axial pumps. The specific speeds have the pumps working most efficiently within the range of 4,000 and 9,000. The flow within a mixed flow pump is, as implied by its name, a mix between axial and mixed because it has flow both in the axial and the radial components.
So I'll also be talking about fans, and fans pump air, gas, and vapor at low rotation speeds. They're also called blowers, boosters, and exhausters. So blowers are located at the system entrance, exhausters at the system exit, and boosters are anywhere within the system. And compressors allow for a larger change in gas density and pressure. There are also axial, radial, and mixed fans, just like pumps, and performance in these flows is the same as pumps as previously discussed. The only difference is that fan performance is measured by pressure rise, while pumps are measured by head rise. And listed here are the specific speed ranges for both the centrifugal fans and the axial fans. And a real world example of this, as seen in the top right corner, is a laptop fan. So we all have this in our computers and laptops, and they go crazy when you have Zoom and a ton of tabs open, but they're necessary.
So I will be touching on turbines. Turbine geometry so that the fluid exerts a torque on the rotor in the direction of rotation to then extract energy from a fluid. And that's kind of the base of a turbine, is they extract energy from the fluids. These can also have axial, radial, or mixed flows, and the specific speed, which Stephanie just touched on as well, is used to approximate which turbine geometry will be the most efficient for certain situations. There's two kinds of turbines, impulse and reaction turbines. Impulse turbines is when the force on the blade is produced only by the turning of the fluid, with all the pressure drop occurring in the fluid nozzle. So the Pelton wheel is just a classic example of this. I feel like we've all seen one of these, whether in our history books or in person. The individual jets of a fluid hitting the buckets is what generates the torque, and the rotor is open. So it's not enclosed in a casing, it's like open to the outside. It's the most efficient with high head and lower flow rate operations. And ideally, the fluid enters and leaves the control volume with no radial component of velocity, but such designs are pretty complex. Next, we have reaction turbines. Force is due to the turning of the fluid and due to a reaction to the fluid's acceleration relative to the vane. So they're a little more complicated than impulse turbines. But the pressure drop and fluid relative speed change across the rotor. And in this case, the rotor is surrounded by a casing that's completely filled with the working flow fluid, so you can't see them, they're all enclosed. These are the most efficient with low head and high flow rate operations. And then to the left, you can see kind of a simplified example of both. Left top is the reaction turbine, and then to the right is an image of the impulse turbine. These are just our references for a few of the pictures, and then most of the rest of the information we got from the textbook. But thank you so much for being with our presentation with us.